Welcome to the lab in computer architecture. I am Nachum Danzig. I am a lecturer at the Jerusalem Academic Center, Lev Jerusalem Academic Center in Jerusalem, Israel. And today we're going to do a guide for implementing functions in MIPS assembly language. How do we create a function in assembly language? Now, this is for problem set 4 in the course that we're offering, and we'll see now what are the requirements for a function to be a function. So let's go directly there. And a function, in order for us to do a function, we have to have parameters. That's one thing that we need to have. Obviously, we're going to use a jump command, because a jump instruction, because we're going to jump to a certain section of code, do a certain procedure, and then jump back. But we need to have also parameters. So the way we're going to do parameters is we're going to have an agreed upon location. We're going to use registers A0 through A3. And those are called A because of the word argument. So in other words, they're arguments for the function, otherwise known as parameters for the function. So we have a possibility of a maximum of 4 parameters for the function. Obviously, we could have a pointer as one of the parameters, and then we could point to an array of data. So we could have unlimited parameters theoretically. But for the sake of our understanding right now, we'll say that there are 4 parameters: A0, A1, A2, and A3. And that's where you put the parameters of the function. So the function will know to look there when it starts running. Then we have to talk about the problem with the registers, because there are 32 registers. Now, theoretically, each function should be able to use all 32 registers. And yet the main program is also using the 32 registers. If there would be a solution. You say, well, the function will just use 10 registers, and then 22 registers will be used by the main function. But that's not good, because I want my function might be very long, and I might need 32 registers. And secondly, my main program might be very long. He may need all 32 registers. And why should I limit myself if I don't have to? So we're going to learn a method that we're going to basically be able to use all 32 registers for the function, even though they're in use by the main function. In other words, we're in the main function, we're doing stuff, we store things in registers, and then we call our function. Our function will be able to use those registers, but without overwriting them. So how are we going to do that? So basically, the solution is to, before we write to any register when we're in our function, before we write just in the function, the main will say the way it was. But when we're in our function, before we write to any register, we'll copy out the value to a temporary array in the data segment, not into registers, not into other registers, but into the data segment. We'll make it essentially an array in the data segment, and we'll copy all the registers that we want to use. We'll copy their values, what they had before we wanted to use them. In other words, their previous values from the main. We'll copy those values into this array, and then we're free to overwrite the registers. Then when we're all done, just before we return from the function, we have to copy back all the data that we stored in the array into the registers where they had previously been residing. So that's our solution. Now, we theoretically could use any array, but we're not going to use any array. We're going to use a specific array or a specific section of the data memory called a stack, and I'll explain how that works. We actually talked about it a little bit, but we'll talk about that. Now, what else does the function have to do before we get to that? Well, obviously, we do the function. We do the procedures in the function. And then we return the values from the stack. That's what we said here. Here we store the stack. We store in the stack the current values of any registers that we are going to write to. Then we do the function. Then we return the values. Then we place the results of the function in an agreed upon location. That's going to be, let me add that in here, that's going to be V0. And if there's 2 return values, which is possible, we could use also V1. But don't use V1 unless there's 2 return values. only use V0. So all the functions should be putting their return values in V0. Stands for value. That's the value the function returns. So those are special registers for special purposes. Now, of course, theoretically, you could use any register, but we want all functions to work the same way. So we know after we call the function, we always will know to look in the V0 to find the result of the function. Now, after I put the value in the agreed upon location, the last thing I have to do is return to the line after the function call. In other words, I need to jump back to wherever I called from, and we'll see how that's going to work. But right now, what I want to talk about is the first part. Well, the agreed upon location, we understand. If you want to see an example here, actually, not here, here. Before I call the function, see here, I'm going to call the function, my function. I'm going to jump. This is a special jump we're going to learn about. But before I call it, I put into A0 and A1 and A2 and A3 whatever values I want. T0, I can copy them in, right? This add the two T0 plus 0 is essentially just saying T0. And add those two together and put them into A0. So A0 will get the value of whatever was in T0. So I'm copying into the parameters all the values that I want. That's what we're going to do before we call the function. Now, in the function, we have to talk about the stack. How are we going to be able to use the registers? So what we do is, well, first of all, let's remind ourselves of what the stack, where the stack is in memory. What is the stack that we're talking about? What is this data memory? So if in my slides for the first part of the course and the lab, slide 22 is this picture of the memory of the computer, and you see it starts at 0 down here and goes all the way up to 7FFFFFF. That's the end. Now, if you see it, this is the word stack over here. This is the stack. And essentially, there's a pointer called the stack pointer, which is pointing to the end here, the very top. And every time we want to put something in this stack, we essentially move that pointer down and then right to the space that we have made available. As we move it down, we make more and more space available, and then we write whatever we want. And when we're done, we simply increase the stack pointer back to starting to the point where he was before, so that I can call another function, and he'll also start at the beginning. That's the stack pointer. Now, and this is the data. Now, remember, this is memory. Just like I can put my arrays over here, I put my program code over here, and I put my arrays over here, all my declarations of data goes here. My stack is in a different place, so I don't overwrite this data. It's over at the end. Now, I made for you a special, like a diagram of how this works. Now, in MIPS, well, first of all, I'll show you in the Mars assembler. Here's the Mars assembler. Here's some program. But what I'm interested in here is SP. That's the stack pointer. And if you notice, he is pointing, well, it should be pointing to 7FFFFFFC. FFC, well, actually, what did I say? I think I said FFF. Yeah, FFF. So it's actually not pointing to the very end in the simulator. It's pointing to EFFC. It's pointing a little bit lower, not quite at the end. But we're not gonna. That's not gonna affect us. Even though it's pointing not to the end, we're gonna think of it as being the end. Now I want to show you a little diagram of how the stack pointer works, just to make it clear what we're going to be doing. Just a second. Here. So in this picture, basically the stack pointer is in Mars, in the Mars simulator, is pointing to this address. In other words, it has the value 7FFFEFFC. Now, if I want to write a register, which is for a register is 4 bytes, 32 bits. And when I write it, I need to make the stack pointer go down from C, which is 12 in hex, right? That's 12, to 8. So that's 12 minus 4 is 8. I push it down. So now I make the stack pointer, I do minus 4 on it, and it becomes this value, EFFE at the end. EFF8 at the end. Now, this block is that address, 7FFFEFF8. This will be EFF9, this will be EFFA, this will be EFFB, and then C will be over here. And we'll imagine that C is the end. So we can't write there. So we do a -4, and now it goes to 8. So now when we do a store word, we give it this value, EFF8. And as store word always does, we give it a value, and then it writes 4 bytes. So it's going to write 1, 2, 3, 4. It's going to write in these 4 bytes in the stack. So that will be enough to store one register's previous value, so that I can overwrite the register now. If I want to store 2, I'll simply do stack -8, and I'll get down to EFF4. And then I'll write the first word in EFF. I'll write the first register that I want to use. I'll write its initial value in 4, 5, 6, and 7. In other words, EFF4, EFF5, EFF6, EFF7. Because remember, it's a write word or a store word. And then I'll write the next one in this block. So similarly, if I wanted to store more, I would go all the way down as much as I want, and it'll keep on going down in increments of 4, and then I'll write in the space that I have made available. Essentially, by subtracting 4, I made these 4 bytes available to store a word in. That is the concept that we're going to do. Now, let's see that example that I wanted to show you. Here's a function, for example, in C++. It's a simple function. It takes 4 parameters, and it does, something not that important, but it does G plus H, the first 2 together, minus the second 2. And it returns the sum that it got. So let's see how this function will be done. So first of all, we need to give the function, we're basically jumping to a location. We're jumping to my function. That's what we're going to call it. And the first thing we need to do is, well, before we can start moving the stack pointer down, we need to write the heart and the heart and the main section of the function. The function is essentially this: take parameter 1 and parameter 2 and add them together and put it in a temporary variable. Then take parameter 3, A2 is parameter 3 and parameter 4, add them together and put them in a temporary variable. Then subtract the first temporary variable, subtract from the first temporary variable the second temporary variable. And put that result in S0, some temporary variable again. And then do a 0 plus S0, copy that temporary location into V0, because V0 is, after all, where the return value must be. That's the essential heart of the program. Ignoring the stack, ignoring how do I get back to where I was called from. Now, when I look at this, I see that I wrote to T0, T1, S0, and I also wrote to V0. But let's ignore V0 for the moment. Because, and basically what we're saying is, the main could have had some value in T0, or in T1, or in S0, and I overwrote them. No. I did something that is going to have an effect, what we call a side effect, on the main program. Maybe he had some very important value in that S0, and I all of a sudden wrote to it. And I don't want to have to look back in the main and try to remember what's going on there. I want to be able to write my function once and forget it. And from now on, treat it as a black box and use it in as many different programs as I want and not have to worry that it's going to have side effects. So I'm going to store, I'm just repeating what I said before. So I'm going to store the previous value of T0. So what I do is I say, listen, I need to store 3 registers that are going to be overwritten. I need to store their previous values. So 3 times 4 is 12. I need 12 spaces. So I take the stack pointer, which is SP. Remember, over here I have a register called SP. It's one of the 32 registers. You can't really use it for any purpose that you would want. It's reserved for pointing to the stack, and it has this address in it. But now I want to change it. I want to lower it, push it down, and open up for myself, make available for myself 3 register spaces to store 3 registers. So what I do is I go down by 12, and then I go to offset 0, and I store the S, whatever its previous value was in the main, I store. I store the T in offset 4, and in offset 8, which is the last 4 bytes that I have made available, I store T1. That doesn't really matter the order. I could switch around the order, but the point is I've made 3 spaces. And now I've stored the previous values of those registers. Now I can enjoy myself and write to these registers as much as I want. knowing full well that I have the value stored in temporary location in the stack. And when I finish my program, I put my value in the return value, and I'm all done. I don't need these registers anymore. So I take the original values that I stored in the stack, and I do a load word. This was a store word. I copy them to the stack. Now I take them from the stack and put them back in the registers so that the main will see the value that he expected to have in T1 and T0 and T. So I reverse the process. And I also have to reverse this process. I have to put the stack pointer back where it was. So that if I call a different function, the stack pointer will again be at the top. Because if everybody just pushes it down, eventually it'll reach the bottom, and I won't be able to push it down anymore. So I have to put it back where it was. Now I want to explain why didn't I store also the V0. I wrote to the V0. I should have stored that. The answer is that V0, the whole purpose of it is when I call a function, I expect V0 to be changed. Because I call the function and I expect it to change the value in V0 so that I can know what the function returned. That's where I expect the return value to be. So the main, when he calls a function, he knows full well that V0 will be overwritten. He wants V0 to be overwritten. So I don't store the original value because by definition there has to be nothing of importance there when I call the function. Now we have to talk about the jump back. Now this is a new jump that we didn't discuss. It's a JRRA. JR is a jump register. It's actually a jump it's not of type J actually. Because if you remember, type J has no register. There's no place for a register. This is either an I type or an R type. But what it does is it says, look inside this register, and there's a 32-bit address there. Jump to that address. So as long as RA has the right value, in other words, wherever I called the function from, that line in code, that location in memory where that line of code is, that address, as long as RA has that, then I'll return to wherever I was called from. Now, why RA? Let's look back over here. There is a register called RA, and here it is. It's register 31. And why is it called RA? Well, it'll tell us if I hover over here. Return address used by function call. RA is short for return address. It means it's meant to be used to store the address of wherever I'm supposed to return to. Now, if you remember, we have a PC. This register we can't write to, but there's a register called PC, and it's pointing to 400,000. Well, remember why that is, because that is the address of the first line of code. Here in this diagram, we saw that the program code starts at 400 hexadecimal, and then it progresses up. It was 404 for the next line of code. The addresses of the lines of code are in this location: 404, 408, 412, etc. So, and who is pointing to that? The PC, the program counter. He is in charge of keeping track of where I am. So let's look at the calling function now. What are we going to do? Essentially, what we want to do is, before we jump to our function, we want to store in RA where to return to. So we have a special command called jump and link, JAL. Jumps to the location of the function and places the address of the next line of code, i.e. the PC, into the register RA. Very useful. In other words, we have a single command that does two things. It not only jumps to the location, that we specified, in other words, the function. It also changes the value in RA. It overwrites whatever value was in RA and puts in it the value of the PC, in other words, the next line of the code. So, for example, if I go to the caller, when I'm calling the function, remember we saw that I put the values in the parameters, and then I do a JAL to my function. Now, what this function does, it does two things. It not only jumps to the location, the label called my function, which we saw over here, this label. Not only does it jump there, it also puts into register RA, the value of the address of this add here, the next line of code. So that when the function goes over here and says jump register to RA, that RA will have the right value. It'll have the value, the address of this line. And this line, I just simply take the return value and copy it into T1 for whatever purposes I may have. So that's the very useful function or instruction JAL, J-A-L. And it does two things. Okay, so we understand now everything here. We explained this. The arguments are in A1 to A0 to A3. The values that are returned are possible two return values, even though C++, for example, only has one return value. Here we have two. But we'll always use V0 if you only have one value. Do not use the same thing with A0s. Do not use A2 for some other function. Use always the first ones. Only if you have 4 parameters would you use all 4. Oh, would you use, only if you have 3 parameters would you ever use A2, for example. If you had 3 parameters, you'd have to use A2. But if you have 2 parameters, you should not be using A2 or A3. Also, I write here that the caller should be able to assume that the parameters he sent are not altered by the function. Therefore, if you're going to alter the parameters, like A0 and A1, you should also save them to the stack. Because when I send a parameter to a function, I shouldn't expect the parameters to be altered by the function. Okay, so just the V will be altered by the function. Now, we have a few conventions which I'm going to tell you about, but I don't actually want you to follow in this course. By convention, we do not really need to preserve the temporary register. So actually, we don't need to store in the stack the T0s to the T9s. That's why they're called T. T for temporary. They don't need to be stored. In other words, if I call a function, I should presume that the function will write over my T's. So I won't have anything of value in my T's when I call a function. But I don't want you to use that. I don't want you to rely on that in the lab. I want you to store all registers in the stack that you change, except for V, obviously. Well, we'll see about the RA. But the S registers are called the save registers. Those, of course, do need to be stored in the stack. That's why they're called S. And here I wrote that same point again. If there are 2 parameters in a function, they must be stored in A0 and A1, not anywhere else. Do not store registers that the function changes in other registers. So some students have tried to do this and say, oh, I'm going to change this register. I'll just store it in a different register. But then you've changed that register, and then that register needs to be stored in this stack. It's like the joke of Chelm that the men came to the rabbis and said, what should we do? We dug a hole, and we have all this dirt. Where should we put the dirt? And the rabbis thought and thought and thought, and then they said, we know, dig another hole and put the dirt from the first hole in the second hole. So obviously this is not going to work because now you have more dirt. So you can't just use another register for storing the value of the previous register, because when that register got changed, you need to store it. So you use the stack. That's just an observation I had. The students were doing that. Now, okay, so we have this program and everything. We understand everything here. We understand why it's a JR. We understand why we stored things in the stack. And why we had to lower the stack and raise the stack over here. Now, I have one more complication. What if somewhere in the middle of this function, from here to here, before we do the return value, we do something like this. Jump and link to my other function. We have some other function called my other function. And we go and do that, and we do whatever we do, and then we come back. Now, this theoretically should still work, right? I mean, it's fine. A function can call another function. Furthermore, a function can call itself. I could do jump, JAL, my function. But let's just talk about my other function. If it does that, which is actually what you're going to have to do in your homework problem, in problem 4, then unbeknownst to you, you have written to the RA. Because remember what we said, the JAL not only jumps, but it also writes to the RA. And it has to write to the RA so that when this function finishes, it'll come back to this line. But if I've written to the RA, then when I do this jump down here to the RA, it's going to be to that RA. The new is going to jump to this location, to this line after this JAL. Now, as I'm going to do my function, I'm going to return to here, come here, and I'm going to do jump RA, and I'm going to come back to this line instead of back to where I was originally called, because I overwrote the original RA, by doing this JAL in the middle of my function. So if I'm going to do that, if I want to do that, which is perfectly legitimate, I'm going to have to store the original RA value. So I'm going to have to go over here and change this from 12 to 16 and store the RA just like I stored the T1 in place, 12. So just remember that even though it doesn't look like I wrote to any register in this line, I actually did. I wrote to the RA, and therefore I need to store the original value and copy it back before I do my JRRA. I'm going to have to copy it back to RA. So that's how, in fact, we're going to be able to implement recursive functions or any function that calls another function. And that's what you have to do in your homework. So now let's look at the homework assignment. I don't have it open, just a second. Here it is. Functions. Write a simple calculator which accepts two numbers from the user in either the operation plus, multiplication, or power. So the power, okay, so, and the multiplication should handle negative numbers. So I should be able to multiply -3 times -3 or -3 times 1. The powers should be able to handle a base that's negative, but a power that's negative you should not handle. That's obviously very hard, and you don't have to do that. But negative bases you should handle. Now, so fine, that's very easy. I can just use the multiply function. So the proviso is that, no, don't use the multi instruction. Rather, what we want you to do is write 3 functions. Write a function to do the add. In other words, write a function that simply takes 2 numbers and returns in V0 the sum of the 2 numbers. Be sure to use JAL and JR. Then write another function that does multiplication. And that function should also return its value in VF and also in V0, and also put its parameters in A0 and A1. And that function, multiplication, should not use mult, but should in fact call add a number of times. Because remember, if I want to multiply 3 times 4, I can simply add 4 3 times. 4 and 4 is 8, plus 4 is 12. So we're going to call the add function to do multiplication. And similarly, the power function will call the previously defined multiplication function. Because if I want to take 3 to the 3rd power, I'll do 3 times 3, and then take the result as 9, and do that time, 9 times 3, and I'll get 27. So if you wrote your multiply function properly, then the power should work properly. So use this, and I want you to use the stack and store any registers that your function alters, any and all registers that your function alters. So let's see how we would start such a program. And I have already started it for you, so let's look at it. I skipped over a little bit, but obviously I'm going to have some kind of input-output strings like please enter a number, please enter a symbol, please enter a number. And let's say I got in the numbers, the number in S0 and S1, and I got in the symbol that he wants to do in S7. Now, in T0, T1, and T2, I've stored the value of of plus and multiply and power. So I can now do BEQ. I can say the S7 that I got, that symbol that I got, what was it? If it's equal to T0, if it's a plus, then jump to the place called add place, where I'm going to start my add function. Now notice, this is not a function call. This is just jumping to a location. There's no JAL here. I'm going to have a JAL for it to be a function. Now, I'm going to do another one. If the symbol that I got was T1, was star, then jump to multiply place. And if the symbol that I got was BEQ equal to T2, then jump to power place. So that should be obvious. Let's go down a little bit. Now let's look at add place. What is add place going to do? Well, notice that I wrote here that I read it into S0 and S1. I theoretically could have read it into A0 and A1, but actually there's a problem with that because you need A0 for the syscalls to print the strings. So I don't want to read it into A0. I want to read it into S0. But now that I've done all my input-output, I need to call my add function. Well, the first thing I need to do to call my add function is copy S0, which is the parameter that I got, the number that he gave me, copy it into A0. And I do that by adding it to 0 and putting it into A0. Now, I also need to copy S1 into A1. Now I've loaded up my parameters, I can call my function, jal add function. Now, assuming I've written that add function, he will return me in V0 the result, and I will now jump to print result. So presumably there's a print result down here. Print result, and I do print V0. Notice how I write a comment there just to save myself time. Later, in other words, later when I can actually just leave it like that for now, and later when I review my program, I can say, oh yeah, I didn't do that yet, and I can just write the lines to print V0. It's always useful, and don't get caught up here. Just write a comment what you want to do there. And it's also, then you can leave the comment and reminds you of what this area of the code does. So print V0, that's like instructions to myself. It's a good style of programming. When you're dealing with complicated things, you want to just say, okay, let's assume I printed the result over there. And that's it. The program ends when I print the result. So, but notice how I do JAL. It does the function, it runs over to add function, and then it comes back here. So I need to, again, jump from here to the print result. I don't want in the function to jump directly to print result, because then it's not a function. Functions always return to wherever they were called from. So I'm not going to jump to print result from the function. I'm going to come back here, and he is going to take me there. He is going to take me to the printing location. Now, if it was multiply, then I go to multiplace. And I'm going to do the same procedure that I did before. I am going to copy the values that he gave me and put them into A0 and A1. And now they're in A0 and A1, Yofi, wonderful. And I jump to multiply function. And again, I jump to print result. And the power will be the same. Copy it, jump to power function, and jump to print result. So now I've got them these are all the callings of the function. I've called the function here, I've called the function here. I wrote the function, I didn't write any functions yet. So let's see how I write the functions. Start with add. Add function is going to be very simple. I'm going to take the two parameters that I got. Remember, I don't have to look at where he stored them because I always know that he stored them in A0 and A1 because that's what he has to do. And I'm going to put the result, here I can use the add, put the result into V0 and jump back to the JR wherever I was called by. That's it. Now, do I have to use the stack here? No, because I did not write to any register except VFS, but VFS I'm supposed to write to. Okay, so that function is finished. Now, what about multiply function? Now, obviously, I'm not going to write this for you because this is your job to think about, but let's start you off. First thing I'm going to do is I'm going to have to do some kind of add to the stack pointer, right? Stack pointer minus, I don't know what yet because I don't know what the function is. Minus 8. I may have to go back and change that. You know, it may be minus 4. It may be something else. Maybe minus 12. Maybe minus 16. I don't know yet, but I'm going to have something where I deal with the stack. Then I'm going to, whatever value, I don't know yet what values I need to store, so I'm going to skip that section and go straight to here. But I do know that I'm going to have to have, at this point, in my multiply function, a jump to add function. And that's exactly what I was talking about before, how a function will have in it a call to another function. Now I'm jumping to the add function, and he is going to look at A0 and A1 and return me the result. Now that result that he gives me back is going to be in V0. But I want to store it in a sum because I'm going to call add and get, the first time I'm going to call it, by the way, think about this. I'm going to call it the first time. A lot of people make a mistake and they say, well, if it's 4 times 5, I'm going to give it 4 and 4 and get 8. That's a mistake because then you've done 2 in one shot. And then what are you going to do the next time? You're going to add 8 and 8, and you're going to get 2. It's not going to work right. So what you want to do is add 0 and 4 the first time. 0 and 4, and then you get the result will be 4, and you'll copy that result into your sum. Sum equals sum plus result that I got back from the function. So it'll be 0 equals 0 plus 4. And then I'll call it again, and I'll give it the value that I have in sum as one of its parameters, and the 4 will be fixed. And I'll do 4 plus the sum. And I'll get 8. And then I'll copy that. Sum equals sum. Well, this is the 4. I'll get sum equals sum plus, oh, sorry. Yeah, sum equals sum plus 4. It depends how I do it, but I'm going to keep on calling it with the old sum. This actually might be a mistake. It might be, now I'm thinking about it, it might be better to do it like that with just 0. Just copy the result because he's going to already do. I'm going to give him 4 and 0. And then he's going to give me back 4. And then next time I'm going to give him 4 and 4. And he's going to give me back 8. And I'm going to copy it to 8. Next I'll give him 8 and 4. And he's going to give me back 12. And I'm going to take this and put this and give him 12 and 4. And he's going to give me back 16. And I'm going to copy the 16 straight into the, I'm not going to add it to what was before. I'm going to add it to 0 and put it into the temporary variable. So that's probably more correct. And so I leave it to you to do figure out the loop, figure out the how much I have to affect the stack, and obviously at the end I'm going to have a JR $RA. I'm going to have at the bottom. That's the basic structure, and the same goes for the power function. Okay, I hope this has been helpful. I hope this gets you on your way, and I hope you have a lot of fun doing it. Okay, all the best.